In this video, we'll step back and consider how to interpret a logistic regression model. Recall our mountain climbing analysis, the goal of which is to model the extent to which a climber's success might depend upon their age. Since success is a binary categorical response variable, we can model this relationship using logistic regression. The results are shown in the coefficient table here. Recall that in logistic regression, we model the uncertainty in the binary response variable, here climber success, on the log odds scale. Thus, from this table we gather that the trend in the log odds of success among climbers can be written as 0.426 minus 0.024 age. This model trend, a line, is drawn below. And we know how to interpret coefficients of a line. First, as usual, the intercept value indicates that among climbers of age 0, which doesn't make any contextual sense, the typical log odds of success is 0.426. The only new thing here is that we're being really careful to remember that this trend line tells us about the log odds of success. Next, since our model trend here is a line, then we can interpret the negative 0.024 age coefficient as the slope of this line. Technically speaking then, negative 0.024 is the difference in the log odds of success per 1 year increase in age, say from x to x plus 1. More meaningfully, for every extra year in age, we expect the log odds of success to decrease by 0.024. Or in 10-year instead of 1-year increments. For every extra 10 years in age, we expect the log odds of success to decrease by 0.24, which is 0.024 times 10. Though we've been taking this for granted, it's important to note here that these drops in the log odds of success are constant. For example, the drop from age 20 to 30 is exactly the same as the drop from age 60 to 70, another 10-year increment in age. In terms of truly understanding and communicating our results, though, it's really tough to work on the log odds scale. Instead, recall that we can convert our log odds model to the odds scale through exponentiation. Similarly, we can also exponentiate the coefficients. The results then need to be interpreted in recognition of the fact that through this exponentiation process, the model trend, again this formula here, becomes non-linear on the odds scale, right? We see a curve here. And even non-linear trends, though, have an intercept. We just have to remember to interpret it on the odds scale. So here, we can think, where does this line eventually cross the odds axis? That's the intercept. Or the typical the typical odds of success among age 0 climbers are 1.531. Next, since our model trend here is not a line, we cannot interpret the transformed age coefficient, 0.976, as a slope. Unlike what we see in a line, the per-year decrease in odds is not constant. For example, the drop in success rate in the 10-year jump from 20 to 30-year-olds is much more dramatic or much greater than the drop in success in another 10-year increment from 60 to 70-year-olds. Instead, for every 1 year increase in age, 0.976 is not the difference in odds, but the odds ratio. Specifically, per 1 year increase in age from, say, x to x plus 1, then 0.976 is the odds at age x plus 1 compared to the odds at age x. In the context of our example here, if we increase age by 1 year, then the odds of success are only 97.6% as big as the year before. Or in 10-year increments, if we multiply the original negative 0.024 coefficient by 10 and then exponentiate, we can see that the odds of success at any age are only 78.7% as big as 10 years before. Let's try to make this idea less abstract through a more specific example. By plugging ages 20 and 30 into our odds model trend, we predicted the odds of success are 0.947 for a 20-year-old, or slightly under 50-50, since the odds are slightly under 1, and the odds are only 0.745 for a 30-year-old. This here is a drop of negative 0.202, so this is our vertical drop of negative 0.202, or a ratio of 0.79. Recall that this 0.79 is the exact odds ratio that we calculated on the previous slide for a 10-year jump in age. Next, consider another 10-year leap. We predict that the odds of success are 0.363 for a 60-year-old and only 0.285 for a 70-year-old. This is a vertical drop down of 0.078, or a ratio of 0.79. Now, compared to the jump from 20 to 30-year-olds, this difference in odds, negative 0.078, is much smaller than it was for 30 versus 20-year-olds, negative 0.202. And we also see that vertical drop is smaller in our visual. But the important thing to notice here is that the ratio is the exact same, 0.79. Again, this reflects a property of the model trend on the odds scale. We don't see constant decreases with 1 year increase in age in terms of differences, but we do in terms of odds ratios. Finally, we saw that we can translate our logistic model of success by age all the way to the probability scale by taking the odds over odds plus 1. Though it spans an impossible age range here, the zoomed out picture on the right really just illustrates the results of our transformation to the probability scale. These result in an S-shaped curve, again that's smushed between the probability range of 0 to 1. Now it's great that this curve actually abides the properties of probability, but it makes things a little bit trickier. First, one thing that is less tricky is that on any scale, our model trend has an intercept, right? It's where our line is when age is 0, or what the probability is when we plug in age equals 0 into the trend line here. When we plug in age equals 0, the results are an intercept of 0.6, which again visually matches up with where the curve is at age 0. So here, it doesn't make sense to interpret age 0 climbers, but we see that the typical probability of success among age 0 climbers is 0.6. Though we can still translate and interpret an intercept for any curve, we unfortunately cannot make sense of the negative 0.024 age coefficient on the probability scale. Mainly, unlike the linear log odds scale, the difference in probability from year to year is not constant. Thus, negative 0.024 is not related to a slope. Further, unlike on the curved odds scale, the ratio in probabilities from year to year is also not constant. Here we see big drops, small drops at this end, small drops at this end. It just keeps on changing throughout. That means that we cannot interpret negative 0.024 as an odds ratio. Putting this all together, the important takeaway here is this. The most meaningful and straightforward way to interpret a logistic regression model is to exponentiate our coefficients and interpret them on the odds scale.